the EHT. So one thing I wanted to maybe move on to, and this is sort of related to what we've talked about with the distributed network of telescopes. Both you and I have used these robotic network of telescopes that seem to be popping up, one of which is a famous one just up the road from you called the Las Cumbres. Why do we care? What's the beauty? What's the utility of having a robotic network of telescopes?
So Las Cumbres Observatory is slightly less than up the road than for me because I work at it. So
Well,
you
on
know.
an EHT scale, it's up the road.
Well, yeah,
Yeah.
I
Well,
guess
sort of,
technically, in terms of wavelengths, it's up the
Yes.
road.
Well,
Um,
okay. It's in the same. The headquarters is in the same state.
yeah, right. Oh yeah, so Las Cumbres Observatory is a robotic telescope, and here is a map of our stations around the world.
There is.
It's not a robotic telescope in the way that, sorry, it's not a global telescope in the way that EHT is, right? The EHT was a bunch of telescopes placed around the world that all function as one giant telescope. The purpose of this is to have a bunch of independent telescopes that all work synchronously to try to always give you an eye in the sky. So one of the biggest issues with observational astronomy is you spend a bunch of money, you set up your telescope, and then 12 hours later the Earth rotates away and it's daytime and you can't do anything except look at sunspots. And then if there's an exciting event going on, especially which is what LCO studies, which are these things called optical transients, which evolve on human timescales, like the timescales of minutes, hours, days, weeks, months. Um, you want to have as much continuous coverage as possible. So having a 12-hour gap is a serious problem. So basically what we do is with the LCO, we try to have a telescope in every time zone around the world. And if we want to have an observation, basically we always have a telescope pointed at any sort of spot in the sky because there's always a part of the LCO that has nighttime. Basically, it's led to our motto, which is this is the real motto of the LCO. I am not making this up. It's we keep you in the dark.
Nice.
Yeah.
Yeah.
No big brother implications there.
No.
Yeah, so that's the big benefit. Having a global telescope network like this, telescope in every time zone, no matter what happens, no matter where it is in the sky, we'll be able to see it. And that's just that has applications to so much of astronomy.
Yeah, no, absolutely. And I like what you've done there. So I think how you've described that is really nice. And so one can imagine observing in Australia, like as you can see here, the big continent down there in the lower right. So when you start way out in Australia and it's nighttime, the sun is going to be rising from the east. So at some point you are going to come to the point where you can no longer observe in Australia. And if you just zoom out slightly, Joseph, yeah. So what can happen is one can move from observing in Australia the same object to then the site up in Tibet and China, assuming the object isn't too far south in the southern hemisphere. And then that site can then take over the observations of the same object. So you can continuously observe these very fast transients that are changing on the level of minutes, seconds, minutes, hours, such as supernovae explosions. And so I know, Joseph, you do a lot of that work. But then as the sun, of course, starts rising, moving from east to west, you can then move over to the site in the Middle East. And then you can obviously move down to the site in South Africa, over to Tenerife and the Canary Islands, and so on until you reach the continental northern and southern Americas. And so what ends up happening is you can get this whole Earth coverage, this longitudinal coverage, and have 12, 15, upwards of maybe 20 hours of nighttime observing in a given stretch. And that's really incredible. I think we prepared a light curve that we can show this effect really quite nicely.
Yeah. So
Oh yeah,
this is the light curve for this is a perfect example of a kind of object where having this coverage was critical to the success of the science. So this is the light curve, or basically how bright the object was as a function of time for an object, a brand new object. This is basically, it was predicted but had never been seen before, for an object called a kilonova, which is the result of the merger of a black hole and a neutron star, or a neutron star and a neutron star. I can never remember. But
I think it's neutron neutron.
I think, yeah, that's what I was thinking too. Neutron. I think. But so what makes a kilonova special is that it's 1,000 times brighter than a regular supernova, which is already a very bright object, already stupidly bright. The story behind this is basically when a neutron star and a neutron star or a neutron star and a black hole merge, they produce this incredibly powerful distortion of space-time that results in something called a gravitational wave, which is a ripple in space and time that emanates outwards from the point of the merge of the collision of the two objects, and travels across the universe until it's detected by these unbelievable instruments, the Laser Interferometric Gravitational Wave Observatory, which you may have heard of, called LIGO. And LIGO can basically tell us roughly where in the sky the event occurred. But the problem is, because we can use other instrumentation. It's called multi-messenger astronomy. So we can use X-ray instrumentation and gamma. If there was a gamma ray burst associated, we can potentially see that, and we can try to narrow down where in the sky this merger took place. And there's a reason we want to do that. The reason we want to do that is because these objects, like this kilonova, will produce an explosion that we can actually see in optical light and track via these light curves and get spectra on, and do these incredibly detailed analyses if we can figure out what was the optical event that corresponded to this thing. So if you hold up your thumb, this is a very challenging problem because of how many galaxies there are. So if you hold up your thumb and sort of look at the area your nail covers, in that area alone, there's like tens and tens of thousands of galaxies. And so, when we narrow down to a big region of the sky, it seems like, oh, we've narrowed it down to 1/100th of the sky. But that's millions and millions of galaxies, each of which we're looking for a tiny dot,
Yeah,
a new star, basically, that's appeared in one of those galaxies. And so, that's a very, very challenging problem, and you need to do it fast. So this light curve, this kilonova, experienced its peak and its drop within just 4 days. And so you need to be able to scan the sky looking at, hundreds of thousands of galaxies, if not millions of galaxies, to try to find this tiny new spot of light. And so because the LCO has a telescope in the dark at all times, literally immediately we were able to begin scanning the likely galaxies for this object. And for this kilonova, we found it in less than a day. I think actually in the time scale of a couple hours of searching, we were able to find this object. And then once we found it, this tiny speck of light, which did we include it? No. So with this tiny speck of light in this hidden faint galaxy where this merger occurred, we were then able to, without any break in the observation, monitor the light curve as a function of time. And that's just completely remarkable. And it allowed us to get this unbelievable data set on this brand new object for the first time, which was made possible by the LCO's ability to just robotically and automatically search the sky for this new object, and then immediately continuously follow up, knowing exactly which site was going to be pointed at the object at all times, collecting data by itself automatically, reducing it, robotically checking if the reduction was good, and if it wasn't, getting more data as much as it could. It's just all this feat of technology came together and allowed us to get a glimpse into this brand new object. Thank you for coming to my TED Talk.
I know, yeah, that's a great TED Talk right there. Okay, we're going to end this and I'll put this up on TED. I think you said a couple of really great things there. I think one of the things that occurs to me as well is it does, these robotic network of telescopes, they don't suffer networks of telescopes. They don't suffer from the frailty of humanity, right? They don't need to sleep. They don't need to go to the bathroom. They don't need to call their mother up and say, "Hi, mother, how are you doing? I haven't spoken to you for a week," that kind of thing. So they don't suffer from all the necessities of humanity that we do. And so, as you rightly said, in terms of not, even if it was just not being at the telescopes or not being able to, evade the sun as the Earth orbit rotates, it's the fact that it can just continuously observe and take really very high quality data on these interesting astronomical objects. So we've mentioned a couple of really interesting things. I think you've summarized the positives really well. I think the fact that these telescopes give you geo-liberty, as we've been calling it, you can observe from anywhere in the world. You can run these telescopes are schedulable. They are controllable via computer code, which one can do these days from anywhere with just a laptop. You can maximize your schedule versus the type of object you're looking at. You can get data at any point of the light curve that you need. That's incredibly efficient. You can also, if you've got multiple sites or sites at similar longitudes, and I would say the site in the Middle East and the site in South Africa are fairly similar in longitude, if one is cloudy and the other isn't, you're still guaranteed your observations, which is really nice, very, very nice, very important. One could say the same thing for the telescopes at Cerro Tololo in Chile and the ones up there in is it in McDonald? I think in Texas they're up at McDonald.
I believe it's McDonald Observatory.
It's
Yeah.
McDonald, yeah. And then of course the ones out there, the one out in Hawaii. So the fact that you can get any similar longitudes means you can afford for one site to be cloudy. Obviously, he mentioned the multi-wavelength aspect to things, so you can observe in different filters. I think that is really important. Multi-color, as we call it in astronomy, multi-wavelength observation is very, very important for helping you to discover what type of object caused the explosion, be it a kilonova or a super energetic supernova. You can distinguish between those types of objects very nicely. You said one interesting term, and astronomers use this term in a very throwaway sense, and it always interests me. We call it data reduction. So we should maybe explain what data reduction really means.
Oh, that's a fantastic point. I did just kind of blow by that.
Yeah.
So whenever you look at a nice astronomy plot showing some data, that is literally 100% of the time never the actual data that's collected, just raw. So for example, when you look at a data point showing how bright an object is, it's just a nice, X coordinate shows you the time, and then the Y coordinate shows you how bright it was. But for example, with a supernova, you can't just look at a supernova and tell you how bright it is. You have to do this complicated process where first you take an image in a bunch of different wavelength bands, but let's say just stick with one filter. So you take an image, and then you have the supernova there. And if it's a type 2, for example, it might be lying inside of a galaxy. And so you have to take your image and do a bunch of calibrations to make it match a template image that doesn't have the supernova in it, which you then subtract off of just to leave the supernova remaining. And now you have an idea of just the light that's coming from the supernova. But depending on your exposure time and your aperture and all this other stuff, your supernova is going to appear brighter or dimmer. And so you have to calibrate how big, literally, the point spread function of the supernova is relative to other stars in the image that you know the brightness of. And then you compare them and you use that to extract an estimate of how bright the supernova is. And so this is a very much an oversimplification, but in order to just get that one data point, you basically have to take an image and understand everything in the image as it compares to your instrument and the galaxy and other pre-existing estimates of the brightnesses of the stars in these incredibly dense star catalogs. And then, and only then, can you get an estimate of the apparent brightness of the supernova. That's not the apparent brightness of the supernova isn't super helpful. What's actually helpful is what's called the absolute magnitude of the object. So you have to do a step further where you have to estimate the distance to the object, often by then taking a spectrum and measuring lines. And so just to get this one data point, the absolute brightness or the real brightness of the object, you have to measure the distance to the object and compare and do all these calculations. And so that's what we refer to when we're talking about reduction, how we reduce a whole image which has the supernova into a single reduced measurement of the brightness of the supernova. That's just one example of data reduction.
Yeah, no, that's a good way of putting it. And of course, one of the big things of data reduction is, in fact, getting rid of the effect of Earth's atmosphere. That tends to be a large part of what we do, and the effect of the instrumentation itself, actually. There is an historical point to this, however. Certainly, when I started, which was about 330 years ago, was that I mean, it was a while. Right? I mean, you're a wee youngster compared to me, but in the early days, so basically, I started in the very early 90s doing this sort of stuff. But you would go to the telescope, you record your data on these big magnetic tapes, and in those days, the airlines let you carry them on board with you. But you'd have these seriously, they did. We'd have these big stack of data tapes like you'd see in the old spy movies. And they represented some quantity of data. Like back then, it was probably like 25 megabytes. And every time you did a data reduction step, you treated the data for the effects of the telescope or the instrumentation or Earth's atmosphere, the data size reduced. It became smaller. And so in each various steps, you got down to eventually a plot or one data point, and that data point was literally a number. Your supernova is magnitude, absolute magnitude, minus 20, whatever the heck the number is, minus 5. It's just one number. And so that is a very much smaller data set than the one you started with. So data reduction was actually, you started here with the raw data, and every time you processed it and got rid of all the effects of the telescope and the instrument and Earth's rotation and the Earth's atmosphere, the number got smaller and smaller and smaller until you ended up with a couple of numbers that you could put on a plot and you'd write the paper. So that, I think that's originally why it was called data reduction.
That's amazing. And I mean, it's still true today. If you're reducing anything into a single data point, it's going to be smaller. Even with the images from the black holes, right? Those are kilobyte images that are being reduced from petabytes of data. So
yeah, that's true.
Wow, so you guys are still using magnetic tape back in the day. Was your first telescope like a droplet of water suspended on your finger?
Not quite that old. I wasn't observing with cavemen. Well, like maybe I was.
Yeah. Simplicico was David James and Galileo et al.
No, that's right. That's right. Yeah. Hey, Galileo, you might want to polish that lens before you start. The very first observing trip I went on was in, I don't know, 92, 93. It was to the 1.9 meter Elizabeth telescope in
92?
92, yeah, 1992.
Oh, wow, so that's like just after the Civil War reconstruction was underway.
Not 1892, as I said. Not quite that old. It was in the Karoo region of South Africa.
guys, David's gray hairs are not from age; they're from me making fun of him.
Yeah, making fun of the fact I have gray hairs. Absolutely.
Sorry.
I put a lot of gel into there, and the hair's looking quite not too old. But yeah, that was real observing, because you move the telescope yourself. Like these days, you tap on the computer keyboard, and the code or the telescope control system just moves it for you. We moved telescopes back then. We had setting circles on the axe drives. It was phenomenal.
Oh God, I can't even do it with like a daub.
Oh God! All right, you and I need to get back together I'll teach you how to move across the night sky. But the one that actually sort of at this point is relevant, however, because that's one of my sort of bugbears against these robotic networks of telescopes, fabulous as they are for up and coming astronomers and for new astronomers. They don't really teach you how to observe. They don't teach you like the conditions of the night sky. They don't teach you of the sort of foibles of the telescope itself, which sort of leads me on to the fact that you have to have really good metadata, weather data, all kinds of quality data to understand your data that comes off these robotic instruments. Otherwise, it can be very hard interpreting the data and doing the data reduction.
I've been doing a lot of astrophotography, both for Astraveo and for personal stuff. And it was kind of astonishing how like, it was kind of like, I knew like terms and, trivia, and I knew what words meant.
Trivia.
It's amazing.
Joseph Farah's trivia night. What is the aperture of this telescope?
But like we're joking, but like it's amazing how useless knowing the surface temperature of Vega was when I was just trying to make a picture of it.
Well, that turns out to be really important, because at Vega the surface temperature of about 10,000 degrees, which means its color.
Yeah, it's hugely important for what we do, like in the work that I do on a day-to-day basis. Hugely important, because Vega is the caliber, absolutely important. But like when I'm trying to like when I'm picking an f-stop to try to collect as much light as possible, nobody told me that just going as low as possible isn't the right thing to do. Or like when I'm learning about seeing and stuff, well, for the stuff we do, we never have to worry about seeing, because and seeing is like the condition of the turbulence of the atmosphere and how it affects the objects you're seeing. But we never have to worry about stuff like that, because like that more affects things like planets, where you're trying to discern particular surface features and you want to do like lucky imaging. So like all this stuff, like what you would consider amateur astrophotography, because I spend most of my time working on either robotic telescopes or global networks where I have all the data presented to me in a nice UV FITS file, I was surprisingly unprepared for actually making images myself. So
Well, not so surprising though, is it, Joseph?
it was surprising to me.
I'm just glad you remembered to take the cover off the top of the telescope.
you, you know, I will never remember to turn the stupid star pointer thing off. The
Oh yeah. Yep.
every time it's good, just the battery's just gonna die one of these days. But I'm sure it
Yeah.
doesn't. I'm sure it doesn't help that, like, I'm sure it doesn't help that. Okay, I'll make fun of your age quite a bit, and I apologize. I also get made fun of my age quite a bit too. In like group meetings, it's just no. It's the source of endless amusement that they will use software packages that are older than I am, or people will be like, oh yeah, that supernova exploded in 2009. Joseph, you were in 5th grade, right? It's like, it's like, okay, guys, it's like, okay.
You know what you should have said is I wasn't in 5th grade when the supernova actually emitted its light. It just took that long to get here.
Exactly. So it is.
Well, I can still remember you making fun of me just not long after we met in the Event Horizon Telescope sort of science meetings, and you were tapping away and they were writing Python code, and we ended up talking about something, and I think it was scheduling of telescopes or something like this. And I had a Fortran code, and you're like, Fortran? What the heck is Fortran? And I know because you love computers that you knew what it was, but NASA used it in the
I
70s
remember
and 80s.
I remember that joke. It was something dinosaur related. Like,
Oh yeah.
10,000 lines of Fortran later.
But yeah, that's right. It's like, oh look, I did this in 3 lines in Python. Like, oh what? Oh
What's the
god.
joke? Python, you can do anything slowly.
Yeah, that's right. That's right. Oh my gosh, that's funny. Well, this sort of all this is relatable though, because the very first time, like I said, my first observing trip was to the South African Astronomical Observatory. I had 2 weeks. First week was on the 1.9, doing 1.9 meter, doing the spectroscopy. I was looking at M dwarfs, actually looking for flares that we talked about last week. I was looking for optical flares and H alpha emission from these X-ray selected M dwarfs. And the second week, I had a week on the 1 meter telescope, and it was to do imaging of an open cluster, Messier 7, my Ptolemy's cluster. And I remember I'd never done imaging before.
Not Messier 87.
No, Messier 7. M7.
Oh, Messier 7. I thought you said Messier
Yeah.
87. I was like, I'm pretty sure that's not an open cluster.
No, Messier 7. It's at the tail of Scorpius. Right, it's right next to.
Yep.
In fact, it's right in the same direction as the galactic center. Very hard to observe because there's so many background stars. So anyway, the spectroscopy. The first week was spectroscopy, which is like taking rainbows of stars. You split the light into its component colors, and I could do that very well. I understood the concept. And the second week was doing photometry, which is just collecting images and working out the colors and temperatures of stars and the brightnesses. Well, I'd never done it before, and I did a bit of reading beforehand. And my supervisor, who was ill at the time, unfortunately, he had non-Hodgkin's lymphoma, so he wasn't able to travel to South Africa with me. He made a full recovery, by the way. Yeah, no, he's still.
Thank God. That's a huge relief to hear.
He's a very, very a lovely astronomer. So I went on my own, although the first week I had a Professor Bromwich. He was this lovely old guy, and he'd been doing astronomy years. And he helped me the first week, but he had to return back to teaching the second week. So they gave me the keys to the dome, and it wasn't the one behind me. This one in the image. This is in Cerro Tololo in Chile, but it was similar, right? The one at the South African Observatory. They gave me the keys to the dome, and he said, "Right, good luck. I'll see you at the airport next week." Or what? I've only used one telescope for 1 week, and you were there the whole week. I said, "Oh, you'll be fine." So they didn't explain how to turn it on, how to start the computer, how to observe anything. So it took me. It was the first night or the first afternoon. It took me like an hour and a half to open the dome, just to figure out the button to open the dome. So eventually, I know it was ridiculous. And I had 7 nights of clear weather. It was lovely. It was cold. It was middle of June, which is
good thing you got the dome open.
Oh, I know. Anyway, so I observed, took all these lovely data of my open cluster. I was able to go back and match up the stars with the X-ray images I had from the ROSAT satellite. And when you turn these images into measuring brightnesses and colors and so on, you have these transformation equations, they're called, and you have to calibrate them. And basically what you're doing is you're basically taking into account the effect of the filters that you use on the telescope and the Earth's atmosphere, which has all kinds of effects on the telescope system. And there's sort of 0 point of where you measure brightness, and that's fundamentally set. And the way you do that is you observe a series of standard stars, and that means their properties are very well known, both in terms of brightness and color and temperature and everything. So when you observe, you take a whole bunch of standard stars, take your science image, take your standard stars. So science calibration, science calibration. Well, nobody told me that. And so the whole week I just took a whole bunch of science stars. I took 50, 80, whatever it was, science stars, science images, thinking I was brilliant. I had all the data, and all this was for my PhD project. I was thinking, this is phenomenal. I'll be just ready to do my PhD. And I was so happy. So I got back and started doing the data reduction, and bought my supervisor, actually, he was a specialist in X-ray astronomy. So he hadn't done photometry either. So I was like, well, I'll look at all the research papers. And there was a great book about photometry. So I looked it all through. And then these equations started coming up about how to calibrate your data. Like, whoa, what do you mean equations to calibrate data? Surely anyway, it turned out you needed observations of all these standard stars. And I hadn't taken one single observation.
Oh my God. I'm getting this story is causing me physical pain.
Oh, it hurts. And so I went back the next year. In fact, I went to a telescope in Australia to do it. I went back the next year and had to do it all again, but this time with calibration stars.
Oh my God. Were you? Oh no.
So it was a very hard lesson to learn. And right now, right here at this, I'm at my dining room table. Right here, right now, I could write out that equation for calibrating stars.
Yeah, I bet that's burned into your memory.
Oh, geez, yeah. I got tattoos on the inside of my eyelids. But
I'm so sorry for your loss.
Oh, yeah. Well, it's a hard lesson to learn, but anyway, but that's, I know it's a very long story, but that relates to the fact that these are sort of robotic networks. They're not very good at teaching students or early career scientists in how to observe. And that sometimes you need that lesson at the telescope to be able to do that.
So all I've learned about standard stars is that when I don't see a standard star pop up in the spectra inbox, I write "no standard star this night" in the comment on the observation. And that's the extent of my standard star knowledge.
Yeah, you really need them, actually. In fact, spectroscopy, you need them as well. You need radio velocity standards. You need telluric standards to remove the effect of Earth's atmosphere from your spectra. Flux standards to see how much light you're getting through. It's very important, actually.
Well, we do, yeah. We use we try to get standards for every spectral observation we do, even more so than the photometry, because we can calibrate the photometry to other stars in the images that are in catalogs, but the spectra you need more more specific, like night by night stuff. I have a quick digression related to your story. I have an image of that region in the Milky Way. Is the Ptolemy cluster in this? I think it's this one, but
yes, that's it. That's it.
Okay, that's super cool.
Yep.
That's
you know how
cool.
you can see it. So this is so what you're looking at here. Actually, zoom back out, please.
I'm sorry.
Yeah. So what you're seeing is, in fact, if you go down toward the mountain, put your cursor down, straight down. Oh no. Yep. A bit farther right. Yep. So there are 4 fairly bright stars above it. 1, 2, and then 1, 2. 1, 2, 1, 2. Those 2 there are called the 2 stars of the Stinger in Scorpio, the constellation Scorpio, and they point straight to M7. So in fact, that's M7 right there. That's my PhD open.
That's so cool.
Yeah, and in fact, if you zoom in a bit more, if you can, I don't know if you can. Maybe, yep. You see, there's a red star there.
Right there.
Yep, that is the only red giant in the open cluster.
That's so cool.
That's the brightest.
Oh my God, I wish my data were better.
Yeah, no, it's a bit of a blurry image, but
a little bit.
Yeah, it's a lovely open cluster, and we talked a little bit about this last week. But open clusters are essentially the timestamps of stellar evolution, because you can measure their ages relatively well. In fact, it's on a relative scale, because it's all relative to the sun, which we can measure the age of the sun with radiocarbon dating of leftovers of the solar nebula. So meteorites. But the open clusters, you can measure systematically, and you can age rank them. Very young star clusters like Orion, for instance, 1, 2, 3 million years old. Slightly older star clusters such as the Pleiades, the Seven Sisters, that's 120 million years old. Up to the Hyades, which is about 600 million years old. That's in the background of V of Taurus, and in the V-shaped constellation of Taurus, the Hyades are scattered in and around the V of Taurus. And then you move to older and older systems. This one's not too bad. This one's M7's 220 million years old. So what we do is we measure star clusters of various ages, and we age rank them, and then we look at the properties as the stars age. So I'm specifically talking about things like rotation, X-ray activity. Lithium turns out to be very, very important for cosmology, actually, all the way up to the age of the sun at 4.5 billion. And there are a couple of older open clusters we look at as well. And then we get this very, very nice age evolution of the properties of stars. So it's always been my passion, actually, to do open clusters. That's how I started. And I still do a bit of work in them now, actually.
And your work on that has been brilliant. And something you guys should know about David, he has a terrifyingly encyclopedic knowledge of like everything in the night sky. It's just insane how you can just, it's ridiculous. You have, don't deny it. You're incredibly, incredibly good at this.
Well, thanks. I'm not bad. Yeah, I'm not bad at star patterns and that kind of thing.
But yeah, so it's so cool that we have you can just look you did your thesis work on this open cluster. Like this just
that's amazing. Yeah. Well, this is the one I took all those images of, that I ended up having to throw away the images because they were just utter rubbish. In fact, you can see this must be Scorpio. In fact, if you look at the top right, there's a very red object.
That's a row of Fuchsias.
No, I don't. Well, row of Fuchsias is right next door to Scorpio, but I think.
So you're talking about the top right of the image, right?
Yeah. This star here.
This is Antares, and then these dust lanes are row of Fuchsias.
Yeah, that's right. It's Antares, but Antares is the brightest star I think it's the brightest star in the constellation Scorpio. And it's Antares is so called because, as most star names are, it's from Latin. Not Latin. That's absolute rubbish. It's from Old Persian, because most of our astronomical knowledge of was sort of reborn in the Renaissance in Europe came from Persia. And so Antares is related to Arabic, and it means the deceiver of Mars.
Oh, whoa. Because it looks like Mars.
It looks like Mars. So Antares means the deceiver of Mars. Mars actually does pass through Scorpio because, of course, it's one of the constellations of the zodiac, which means the sun's path passes through that constellation.
I always have a terrible week when Mars passes through Scorpio.
Oh, indeed. Terrible week. It's very beautiful, however, because you see Mars and Antares juxtaposed, and they're just beautiful.
We got to get a shot this summer.
Yeah, let's try and do if depending on if Mars's orbit plays nicely, we can do that, because it's a beautiful image.
But so is Scorpio just stretches across this whole image then?
Yeah, it's a really big constellation actually on the night sky.
Wow, I didn't realize that looking at this actually.
Yeah, absolutely. Well, you can sort of see the S-shaped tail of the Scorpion, because the two stars I identified as the Stinger, and then it goes in an S shape, but it actually goes below the horizon and then comes back up. And in fact, you can see the tail coming back up in that very bright star. No, not that one, other side, coming up from the mountain.
This one.
That one, and the one right coming up right by the mountain.
This one?
Yep, that one. So it's like an S shape.
Is that not another open cluster? This one?
It actually does look like an open cluster. You're quite right.
There's a bunch of these. There's a Ptolemy, of course, and then there's the butterfly cluster.
Yes.
Which creatively named.
M6 or M8? I can't remember which. Oh no, M8 is M8 is Lagoon, I think.
Yeah, Lagoon is up here.
Yeah, there you go. There's Lagoon. Yep.
Lagoon, I think the Eagle Nebula.
Yeah, M6, M16 and M18. Yeah, I've observed both of those.
Yeah. What haven't you observed, David, to be honest?
Yeah, I've observed most of the sky. But this